lot of trial and errors. Yes, and it also depends on the environment that you are doing. Supposedly, you are accomplishing a well. Yes, now you may not be able to accomplish the same well tomorrow because of the environmental effect. And also, it is time consuming. Like you are doing it one ampere, two ampere, if your range of the supposedly current is 100 ampere, then you have to try doing it at this various ampere and then you have to select at what ampere you have obtained a good well joint. Yes, that well joint also needs to be tested. A good well joint is only by visible through your naked eye. But after that, several testings have to be done. If you will need a good tensile test, good strength material, then you have to go to the tensile test. If you need a good hardness material, then you have to go to the hardness testing. So all these things are taken physically, and it is consuming a lot of time as well as resources. So nowadays, what it is that the whole procedure is what that may virtual do. That is through some simulation software or through some coding, it is done where now not only the welding process. Okay, now we are where you have what done given all the physical phenomena that is already told. That is the heat source, heating and surface, and melting, and the expansion and contraction. Everything is assumed there. Yes, and then what? Depending on that, what type of zone you form, what might be the dimension, and the testing also can be done. That tensile testing can be done in a virtual mode in the same specimen, and that saves a lot of time and especially resources. Because if you are using low cost material, it is nothing. But if you are using some super alloys or some very costly material like titanium, so a lot of risk we cannot. Effort to lose so much of resource, so much of material. So the virtual mode is the main important aspect. So in the long term, what is the main long term objective is to permit a universal concept for simulation of the entire process chain based on the basis of elements consisting of process simulation, structural simulation, and material simulation. That is what I put not only do the simulate the welding process, but we do the testing by giving all the control and mechanical properties, and you can define how fracture. Fracture is also done. Fracture, the fracture toughness and the theoretical J. All of these can be calculated, can be simulated through the through some software or through some coding, where material properties thus can be defined. So everything can be done with the project. So by that it tells you. Supposedly you know that some track are there. So how much time the same material you are supposedly passing, you have welded some circular cylindrical part and then you are passing some fluid. The fluid is also exerting pressure on it, and if some cracks has already remained there. So how much long you can sustain? How much long the cylindrical part is sustain? And then with pressure, you can give what the valves, boundary valves are there. One time of how much time it can sustain it by so all this can be simulated. That is not much. This is not and the component. So where simulation is very important phenomenon. Now, what are the softwares available? Now, future coding, C++, coding they are the main softwares that are available and is based on one single modeling approach, that is finite element approach. ANSYS, Abacus, C12 processes are available. Now, what are the methods that have been utilized since decades for what? Joining the for solving the engineering problem. One is the analytical method, one is the numerical method, and one is the experimental method. As I have already told, you can in the whole range you can do trial and errors. Yes, but that is very expensive because and only physical prototype will 3 to 5 first you have to make before making the main product. You have to for one single parameter you have to do the welding. इससे अच्छा होता है कि you have not got a good welding there, then you can perform the same experiment 2 3 times to ensure that this is a good welder. That only you can apply to the main method at 8%. But in analytical method, what you do, the second equation proposed for heat, for calculating the temperature, the Fourier heat law is the basic equation, governing equation. So what do? You try to solve it, yes, and then you try to apply properties, yes, in numerical methods. And next is the numerical method. That is already some mathematical representation will be there. You will be either approximating the circuit, the well zone, or you will be approximating the well zone into small elements or into small volume, or you will be finding out the difference between what 2 points, yes, 2 points in the well line, and then you will be solving something. So that becomes very easy because in this software also all the basic governing equation are already inbuilt. All you need to do is to put some process parameters and test it in the virtual boot itself. So this numerical methods are mostly useless and this is very useful. How we can it by comparing the simulated result with the experimental one. So these are the various numerical methods that are available. One is the finite difference depending on it is based on the solving the differential equation. Means the difference between two points supposedly will be considered inside the well volume and the difference in the 2 points. Yeah, all the properties and the physical properties different between the 2 points will be calculated. And in the finite element method, what shape functions are there? Different functions can exist. Click elements can exist. Yeah, like different types of elements can be achieved. Yes, one can be the brick element, one can be the tetragonal element, so hexagonal element. So there are different elements. By this, you you divide your value into various elements. Yes, the number, even the more the number of elements, the more precise joining can be done. And if you are supposedly you are taking a Greek element, your cube it will be like cube. Yes, so what the difference? Then there will be how much? Then there will be 8 corners. Yes, and then you can find out the temperature at these 8 corners. And each element, so the 8 corners can have different degrees of freedom. So understanding this is a little complex, but it is an easier one. Yes. So all these things, the different nodes, and the different nodes, what type of degrees of freedoms and what type of functions will be there. So the shape function. So this is an important phenomenon in finite element modeling. And one is the finite volume. That is the whole well zone is divided into control volume. That is certain volumes it will be divided. Then here you can calculate all the things, the temperature not at a certain node, not at a certain point, but here as a over the whole control volume only. Means like wherever you are getting the whole volume, the temperature of the whole volume can be calculated as a whole. So all these approximations are there. Now let us come how the finite element. I will be focusing on some results that I did to the finite element software, that is Abacus. Or this is the same approach in every finite element software or in coding. So what is the main basic part? It is you first have to decide the reason is focus to a small focus area. So what you need to decide? You first need to decide the heat source mode. Now what do you understand by the heat source mode? Like the laser is being focused to a small area. Now what type of well being is formed? Yes, so the well being sometimes can be what semicircular, sometimes it can represent full penetration, that is it can represent keyboard that it can represent different shapes can be there. That I will show you on the next slide, but sometimes depending on the power now this is happening in a hourglass application process. Laser beam can be of different shapes and size, and it can be conical in shape. Yes, so depending on that, you assume different heat source model. Yes, so which after the simulation must be able to replicate the zone that you have found so by the experimental means. Yes. So first most important thing that you need to decide is the heat source model. Then you do the common simulation means by giving the boundary condition means the first important thing is the initial condition. What is the initial environment? Where your base material is. Supposedly you are doing underwater welding. So what is the degree of temperature of the water? Yes, where if you are doing it there, what is the temperature? If you are doing it in a very cold environment, what is the temperature? So the initial temperature must be predefined. And then the boundary condition. Like in the welding, you will be using different jigs and fixtures to hold it so that it does not get displaced during the welding process. So these boundary conditions need to be incorporated into the model, into the plane that you were trying to simulate. So given the boundary condition and the good proper boundary condition without much approximation is a important necessity for the success of the simulation. So then we will be giving the temperature dependent physical and mechanical properties. Yes, for then temperature dependent temperature dependent specific heat, temperature dependent thermal expansion, the density you must define, and all these properties need to be defined, and the process parameters then you will be giving like how much laser power you have used, yes, and the properties can be defined in the heat source model. Yes, the power, the voltage, the current that has been used is defined through the heat source model. Then, after simulation, now you will be obtaining time temperature profile. You will be obtaining the cooling rate that can be done. The temperature development during the entire process. So it is not visible here. So what are the various laser process? Number one is the laser power. Number two is the energy density, the power area. Number three, if you are using it pulse mode, so what is the pulse rate? Means for how much time you will keep the laser on and for how much time you will keep the laser in a very low mode so that it does not fall upon the surface. So one will be the laser scanning speed. Means like if you are moving the laser from one end to other, or if you are moving the workpiece from one end to the other, so that the laser scan its entire weld area in a line. So the laser scanning speed is an important phenomenon. So all these things defines your electrical process parameters. So now you must understand first what are the process parameter must be used for joining. In microwelding, definitely process parameter will be having a smaller value, but you must understand the interactive effect of this process parameter. Means like if you are using only laser power and then the laser speed will also vary. Yes, at a certain laser speed, you have to vary the laser power. That is okay. But if simultaneously the laser speed is also varied, then different effects will be there. So the interactive effect of the laser power, laser velocity, laser density, all these things is a must. Not only the individual effect, not only the laser power effect on the welder, but all these process parameters taken together must define your weld joint. Yes, so here the graph shows you that below certain power, yes, below certain power, your energy density will be low, and so I will be just showing you one slide where production welding and keyhole welding will be defined. But here there will be certain certain stable zone that is marked by the red lines. That is, you will be obtaining full penetration welding, and full penetration welding is assumed to be a good welding, strong welding. So here where it must have sufficient power and it must have what very not very high speed, so that the heat reaches the weld joint and the heating and the joining is accomplished. So, what are the physical aspects now? Let us see. This is what conduction mode and the keyhole mode. So, just I will just defining it, not get much into its physics. So, what is it? The laser has certain intensity. Yes. So, if its energy density, that is heat per unit area, is less than 70.6 watt per centimeter square, then conduction mode can be accomplished. That is conduction mode where the penetration is less, but the well width is large. Yes, that is, it depends why, because the buoyancy that is defined mainly because of the buoyancy force and or the surface tension force. If it is velocity, a lot of fluid will be there, and how the fluid is moving during this welding process. Yes, in a molten state, how the metal is moving defines it directly. Now next, the keyhole mode. In the keyhole mode, the laser power density will be greater than 10 to the power of 6 gram per centimeter square. Here, what molten material will start evaporizing. Yes? Because the energy density is very high, you focus a very small area, and then the material will the temperature that is reached will be much more than the melting temperature, and at that state it will start vaporizing. So when it starts vaporizing, the gas, what? Then a dying wood type of a thing forms. That is the 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 molten material will exert some vapor phase pressure in the downward direction and blow. Like when you blow some liquid fluid, then what happens? One both type of things you observe. Similar is the case. The vapor pressure will be giving some pressure on the liquid, on the molten liquid, and as such, but that penetration will be increased. So this is just the basic routine. So in this case, you will be obtaining a very deeper porosity. Now it is look into the theoretical background, as I was already saying. That is the Bobonic equations. So what is the main Bobonic equation which governs the temperature development inside the welder? It is the same. The Fourier heat law. You have already, I think most of you already know it. That is the variation of temperature in spatial and temporal bound. That is, the space will be the temperature is varying. That is in x, y, z direction the temperature is varying, and with time also the temperature varies. Okay. Now if with time the temperature is constant. Yes, the constant temperature, then it is called steady state. But in welding, the temperature varies with time. Yes, supposedly you are carrying the laser from one end of the plate to the other end. So at the very first point the laser is carrying it, that is the peak temperature at that point will be high. But in the central point, what will be the peak temperature? Low. Yes, so as the laser head is moving from the start point towards the center, but the temperature of the central point will be there. Initially it was 0, but as the heat source is approaching it from the initial line, what its temperature will gradually increase. And when the laser heat source focuses on the central point, its peak temperature will be the highest, and after it has moved from the central point towards the end point, again its temperature will start reducing. So the heat source, when the heat source is at the central point, its peak temperature is the highest. That is the temperature at the certain point is what? Based on time. It is dependent on time. So it is called transient temperature distribution. Yes. And then the second one is the boundary condition. Yes, that is where conduction will take place, where convection will take place, where radiation will take place. You assume that where the surface where it is focused, all the three type of things are happening: conduction, convection, and radiation. Okay, so it will make more clear through a diagram. So all these three phenomena combined together will define the boundary condition. Now the initial condition, as I have already told, at what temperature and what environment you are welding in will define your what theoretical will define your at the base between what it must be defined, it must be predefined. Now the heat flux. Heat flux is nothing but the heat source that you are using. This equation shows you only the what 2D heat flux. Yes, like only the heat flux that is focused on the surface. Yes, and as it is focused on the surface, whatever weight it has taken is taken. But generally, what is more preferred? Defining the heat flux in a volumetric expression. Yes, so that is lot of heat fluxes are there. That is double ellipsoidal heat flux. I think Classes will be explaining that one in the next session. So double ellipsoidal flux is there, conical flux is there, and then heat source heat hourglass model is there. So lot of models has been developed. But here we have shown only the surface heat flux. Here two represent the you must know that I think it will be the laser is being focused on the surface with a Gaussian heat distribution. That is, the heat distribution from the tip of the heat source is gradually increasing towards the what? Towards the focusing surface. Yes, and here you can find out. Yes, the mushy zone represent what? The value. Yes, so all these things need to be considered. So the if it is very steep, the Gaussian distribution, that is the inverted U type of a thing, inverted V type of a thing. Yes, so here it is already shown. So if it is very steep, then the distribution, that is the two here will be different. If it is a little bit broader, yes, that is the focusing area is more, and it is not very steep. Yes, then it will become what? 3. The it will gradually increase. Yes, so this is what an efficiency. Now the second term that is representing the efficiency. What do you mean by efficiency? Efficiency of a laser must be defined. But we know the efficiency of a laser heat source for welding is very low. I am not telling about the whole process. But the laser heat it has absorbed. Supposedly you have given 100 power, but it will be able to use the least laser heat power of a small amount of this laser heat power. Actually, whatever you apply, the heat input received by the material for melting will be what? Very low. It is generally to the range of 0.40%. Only 40% of the total heat that is supplied by the laser surface can be utilized for the actual heating and the melting process. So defining the efficiency is also very important. Yes. So here you have seen what the first part that is shown is here you can see that the whole plate is divided into certain what meshy zone. Yes, different mesh elements it has been divided into. Now the first part which is looking darker here why? Because the elements are very small size. Yes, and so denser. So यहाँ पर what is happening here? So here the elements are more smaller and more denser. Why? And this represents the value. where the laser heat source is scanning it, and as we move away from the laser heat source, the elements are becoming bigger and bigger. Why so? Because this is so that is the meshing here is done in a non-uniform way. Why? So that the time can be reduced. Because if you do in a heavy meshing throughout the throughout the plate, then what lot of computational time will be there. Yes, to reduce the computational time, when you will be running the program, it must be completed at a lesser time. So you only consider the efficiency of the elements. You only increase the meshing in the well. Yes, and as we move away, the mesh becomes insignificant. So the non-uniform meshing is followed here, and also you can see on which surface convection is taking place, which is open to the air. So open to the air means the heat is distributed to air, and some surface will be connected to the fixture. Supposedly you are using a high thermal conductivity fixture like copper, then you have to define convection coefficient difference. If you are using only mild steel fixture to hold the plate, then you have to use different heat convection coefficient. In a similar way, radiation is also taking place, and from the top surface to the lower, how the heat is conducted is a plus, and the heat loss is convection and radiation, which you have to minus it from the heat conduction. So all these things, the summed up together defines the well zone, which needs to be defined very carefully while considering the well zone. Yes. So this is one of the situation which is so near. Yes. Here what we are doing here, we are showing that heat sources for three different materials. Yes. That is how the material properties are varied from one end to the other. Sorry, here it will not be ampere, but it will be what power. Supposedly I just by mistake. So what it will be happening for a titanium which has very low heat thermal conductivity. So it will be focusing the heat that is received by heat to a smaller area. But for with stainless steel, the top surface is stainless steel and the middle surface is what mild steel. For mild steel, what will be happening is thermal conductivity is large, very much larger than what titanium. So what it will be doing? It will be conducting away the heat. So the heat, the area which is being affected by the laser heat source will be more, as is also revealed by the second diagram. So this is how the simulation part will occur. Here the red zone defines the melting zone, that is more than the melting temperature. So if the melting temperature of steel is 1500 degrees Celsius, in the red zone it will be plus 1500 degrees Celsius. So here you must note down all the temperature, that is the liquidus temperature, the solidus temperature, the microstructural difference temperature, okay, recrystallization, so all these zones in different colors represent different temperature distribution. So now from here, how will we finding out? This is how this rate will do. Yes, the third diagram into graph, it is shown that as you are moving, 0 represents the initial state, then as you are moving and the welding is completed, time temperature for the welding is completed in 30 seconds. Yeah, and at the end you are seeing that peak temperature is the highest. Why? Because the torch is the heat is abruptly ended there. Yes, so you are seeing that at this abruptly the peak temperature gradually is abrupt rising. Otherwise, during the welding you can see the peak temperature is almost constant at 5 at 10 seconds, at 15 seconds, at 20 seconds, the temperature is almost constant. So why? Because the welding process, though it is a transient process, it has received equilibrium. At the start point and at the end point, the temperature is almost constant. Yeah, and the heating rate and the cooling rate is also almost constant for similar plate material. So this is how you can compute it. Yes. So and in the second, the last diagram with different colors it represent that this is the first, the third diagram represents the time temperature plot in the longitudinal direction. That is from the start to the end. But at the last plate it represents the time temperature plot along the transient, मतलब center point meaning in the center point how you are taking from see at 0 degrees Celsius, which is representing the peak temperature that is at the center line you are taking, and as you are moving away from the center line, what the temperature is gradually decreasing. And the last dark green color, that is 6 mm, the temperature is almost very less. So here you can see this is for titanium. That is the melting point is around 1900 Kelvin. So at around 1500 only no melting will be there, that will be heat affected zone. By this you can find it out. And up to what zone will be the weld zone, up to what zone will be the fusion zone. Here I'm showing you have used pulse laser and how this radiation will be there. The blue color here represent what? They represent that you are not, this is continuous welding. Okay, you are approximate, though you are applying laser pulse, but you are approximating it as a constant continuous curve. And for the peak curve, you have to, what the heat flux that you are considering, you will be considering that it is falling, that is between 20 into 1. But when you are considering the continuous, then for the one will be on time of the laser, one will be off time of the laser. In the on time, you will be equalizing, equalizing the heat flux as 1. That is, it is falling on the surface. And in the off time, off time, you will be equalizing as a 0. So this is one important consideration. The for
Yeah. Yes, your voice clear. Your voice is very clear. Yeah, you can speak.
Okay. So now next will be heat transfer and fluid flow model. The earlier model was neglecting the term that is a fluid flow term. That is the various forces that are acting on it. As I already told, buoyancy force, surface tension force, the viscous force, all these forces are neglected in the earlier convection model. Yes, conduction model. Here this is a convection model. Means you are taking into account the fluid flow. What will be its difference? In earlier, the governing equation is only the Fourier wave law. But here, what is the governing equation? Is the mass conservation equation. That is the mass flow rate is constant. Yes. So the second is the momentum equation. Yes. And third is the energy density. That is the Fourier equation. So here, how these are the various three equations that you must integrate and that you must solve together. Yes. So here, in the momentum equation, takes into account the various pressure, various forces that are acting on it. Yes, and the energy density equation, energy equation takes into account again the temperature variation in xyz direction and the temperature, with n. So all these things you have to solve it. But here what? Three type of assumptions are done. That is a Newtonian fluid, it is a laminar fluid. Yes. So what do you mean by Newtonian fluid? That is the shear stress and the shear strain that is there happening. That is because one surface will be solid and one surface will be liquid. Yes. So what? The boundary, when you are welding it, only the small portion will be melted. The boundary of the base material will be in a solid state. Yes. So that is the boundary. That the boundary will be exerting some pressure. Yes. So all these things. So stress and strain will be taking place, shear stress, because the liquid will be not only deforming in a longitudinal but some shear deformations can be there. Yes, shear will change its shape. Yes, so that shear stress by shear strain of the liquid. Yes, it will be what? It will be linear. Yes, the more the stress, the higher will be the shear strain developed. So this phenomenon is a bit difficult to understand, but it needs extensive solving. Yes, so that is concept. So you are considering it like and no turbulence exists. That is the Reynolds number is lower here. Yes, so it is considered as a flat plate also. So this is one of the boundary conditions that you are considering. Yes, so all these things you have to take into account carefully. So, what are the things that you must know while doing the group analysis is the dimension coordinate, you know, the nodal coordinate, what is the nodal coordinate? Since we have divided the whole plate into certain small element in finite element method, so the each supposing in a cube, that cube will be having how much 8 corners. So each corner is called a node. Yes, so that nodes, the coordinate you must know. That is if the first node is 0, 0, 0, the second node where it will be, and the shape function. Like there will be certain way how to solve it. So the shape function value you must know. That is the dependence of one node, interpolation of one node with respect to the other. Yes, the process parameters that are very important. Yes, then what is the uncertain parameters? What do you mean by that? Certain parameters like efficiency you cannot you have to take that depends on the beam size. Yes, and volumetric efficiency, that is the efficiency that I was saying that laser efficiency is very low. Yes, but the effective thermal conductivity. Now you know that thermal conductivity of titanium is something, thermal conductivity of stainless steel is something, you know thermal conductivity of mild steel is much higher. Yes, but do you know in the molten state what will be the thermal conductivity? Because in the molten state, it will be immediately molten, that is the temperature will be very high and the temperature will be then gradually decreasing. So you cannot define the thermal conductivity very approximately. So you must give the temperature dependent thermal conductivity. But what is exactly the thermal conductivity is an uncertain parameter. So you need to do the optimization of the well so as to find out the most effective thermal conductivity, the effective value of the viscosity, because for a liquid it is okay. But with temperature, the viscosity also vary. So that is the transient temperature exists in the well zone. So the effective measurement of all these thermal properties is also important. So for this, you integrate your fluid flow model with some optimization tools. The various optimization tools are there. So all these things you need to consider. Now here it is shown here. That is you are seeing 1880 degrees Celsius. Yes, this is for what? Stainless steel. Suppose up to 1700 it will be melting. Yes, and then the green zone represents what? Only the where the recrystallization has occurred. So for the different temperature range you must understand for each material. Each material there will be different solidus temperature, there will be different recrystallization temperature, there will be different supposedly for stainless steel it will cool it down, for steel it will cool it down suddenly. If the cooling rate is very high, martensitic structure will form. If the cooling rate is low, then what? Austenitic structure will form. So depending on that, similarly titanium, it was alpha. Supposedly you are using titanium 5, it was in alpha beta range, but as it is melted, it completely transformed into beta range, and as it is cooled, depending on the cooling rate, it will be forming alpha martensitic structure or alpha laminar. So all these things depend on the various temperature field, and as well as it also depends on the velocity. The arrow line here shows the velocity region. Yes, so it is moving away. It is moving in a clockwise direction, and it is moving away from the center of the well towards the outer surface. So equilibrium moving outwards means this welding is covered not the keyhole type. It is the conduction type because the buoyancy force is acting upward and it is in the moving outward direction. And also the surface tension force also exerted is different. So you must know not only the temperature field but the velocity, the movement of the liquid, the movement of the molten metal is also important to take into account. So the this is an important thing that you must effect of what various parameters. How you define the various parameters. One is the Piclet number. What is the Piclet number? Piclet number is nothing but gives you the ratio of the heat, heat convection by heat conduction. Means heat how much the conduction model with and the convection model. Now, depending on the value of Piclet number, you can assume whether convection must be taken into account or conduction is sufficient to define the well characteristics. So, this is important. If the Piclet number is greater than 1, then what? Then convection is a must. Yes, convection is very important. The fluid flow analysis must be taken into account. Buoyancy must be taken into account. Now, the one important thing I forgot to tell is that it is an incompressible plate. That is the density that is not varied. Though temperature is varying, your density is not assumed to vary. Then how the buoyancy is included? The buoyancy is included in the fluid flow through some Bossinger equations. Okay, that is at the point the temperature might vary. Though the density is same, so by at the approximate instantaneous point, the density may vary, and that by that the buoyancy force is taken into account. Yes, so the Piclet number is important. Now the Reynolds number is important. Yes, so how you define the Reynolds number? Why it is important? Because it is important so that it shows you the what the
This lecture is
if it is more, if the Reynolds number is more than a specific term, then the turbulence will be there, and that turbulence will definitely disturb your well tool. Yes, and proper well zone may not be happening. Yes. Now, what is the graph of zero? Zero represents the Gaussian formula. That is the ratio of the viscous force. So the importance that is important to consider. The buoyancy force or the viscous force. So all these terms must be calculated with respect to the process parameters. Yes. So here how the process parameters, that is different process parameters here. Here G in Grashof number, the G represents the gravitational acceleration. Means what type of velocity field will be there. So by gravity, how much field is acceleration will be generated. Then the beta represents the thermal expansion coefficient. So the temperature difference and the what the density of the two and LB is nothing but the well after no what is the length of the well yes through which this buoyancy force is operating. So these are the various terms that are needed to be defined. Now let us understand how this if I was telling that by plastic joining you are what joining your plate. Yes. So what is the important parameter that you must know? That's the last thing I will be telling you. Just 5 minutes more, yeah, sir. So was the same for your heat conduction equation, but here what? Here heat flux is assumed at the transparent, that is a top surface for joining the polymeric material. The heat flux is assumed to be zero there. Then all the heat flux equation, whatever equation you use, you assume it to be focused at the top surface of the lower material and whatever heat is conducted. Now here two parameters is important. The gap length, yes, if there is any gap, and also the roughness factor. Because no matter how much time you have clamp the two pieces together, there will be always certain gap between the mounting sector. Okay, so this is how we take the consideration. So here and in the roughness, when you are taking into account the roughness thing, then what is most important? What is the temperature of the pieces? The thing is that here it is more clear. Supposedly, the joining is taking place as you were seeing at the interface. Now, what is the temperature at the interface? So, due to the after certain gap will definitely be there at the microwave. So, the air will be there. That air, or if you are doing the water will be there. So, what is its temperature? How do you do it? You do it by taking the mean of the temperature of the lower surface, which is definitely the mode, and the upper surface. The initial stage where the temperature of the upper surface is 0 and temperature of the lower surface where the laser is assumed to focus and absorb all the rays is highest. And then gradually the temperature of the upper surface increases and of the lower surface decreases. How? Because it starts conducting the heat away towards this lower surface. So in this way, in the middle, how much air, what is the air temperature is calculated, and then it is incorporated into the model equation. Yes, was it convection occurring there, how much is with radiation occurring there. So, some coding you can incorporate it by taking into account the temperature developed at the two surface. So here it is seen that melting is occurring only at the lower surface and heat is conducting away. So this is how, and this is dissimilar joint. The titanium is being joined to polygonum. That is one of the plastic material. So how this is accomplished? So here it is shown here by this equation. In this equation, what is the most important thing that you must know? The gap conduction. Like how much heat is conducted from the lower surface to the top surface. So these are the so all this is I think already done. So ultrashot laser. Now one important application of laser microwave is that it can be done at a very faster rate. That is the laser I was talking about. Here the laser is scanned in milliseconds. Yes, laser is scanning the surface of the well of the base material in milliseconds. Or you can use laser where you can scan the surface in nanoseconds. In femtoseconds to picosecond. That is 10 to the power of minus 9 to 10 to the power of minus 12. That you must realize how much faster the laser can be. Here the laser can scan the surface in so this is one application of laser. So the heat input that is falling on a certain surface will be very low, though the intensity is high. Yes. So this way you can utilize laser for microwaving. Yes. And one important advantage is seamless, high speed, accurate, and discrete one pulse welding. Means here what does it mean? You single pass of a larger seconds. Yes, you don't provide throughout the surface from one end to the other. When you are using fast laser welding, you will be on it for some time laser beam, then you will be off. You will be switching off it for the some time. But here only you will just single pass. Now that is not very high. That and it will be what hitting out the whole surface. So this shadow method is to be utilized for joining very thin components of watch and various metals and alloys. So one advantage in laser microwelding is the twist. Here it is nothing but the same scanning laser transmission welding where the laser is given in different not in a straight line but in either the coil form or in different scanning. That is nothing but the scanning line difference. Okay, the laser transmission welding which I am talking is slower, scan for a single line. Here it is scanned spirally, it is scanned for like a coil. So how it is utilized is what we need to understand. So these are the various methods. So now laser is being hybridized with some other technology and then it is utilized. So one laser can be hybridized, but and can be utilized. Now, most important application of candidate laser of laser hybrid in microwelding is the use of NDF laser with fiber laser. The fiber laser has very high energy density and can be focused with very small spot, and that eliminates the use of any additive. As I have told in laser transmission, you need additives to be utilized. So the laser, fiber laser, earlier the ambient laser were mainly utilized for laser transmission welding, but now fiber laser is increasingly applied because due to its high energy density, what its this is in the use of additive is eliminated. So the combination of ambient laser and fiber laser is being tried, yes, as a hybrid process, and new capabilities are brought now. So I would like to say that the current development is that the laser has been utilized for very due to its, as it can be focused to a very small area, so very high conductive material can be welded. Yes, so copper is having very high conductivity, so that also can be. So it is joining by welding is very difficult. Yes, but still it has been properly utilized by laser. Yes, and it has been utilized for joining polymers and all. So what are the future challenges? So we must know what type of the heat source. We must first understand the different heat source, and what are the polymeric. The polymeric material is finite. For the present scenario, I have in my slide the simple basically, yes, and now what are the numerical simulation, and this study might help you to know the different advantages of microwelding, also how the simulation can be utilized. Okay, thank you.
Thank you, Mayuri. So, if you participants, if you have any questions, please post in the meeting chat so that I can convey to the speaker. Yeah. One question from Irfana Khat. Irfana, apart from the time constraint, everything is good. Nice presentation. Okay, okay. So
Yeah.
I thought of time constraint means she's asking about this simulation related question, but she's saying about this time. Okay, sometimes it happens for Irfana. Uh, we'll wait for 1 more minute or 30 seconds for this one. Questions? Um, yeah, one question from Vinay. How do we simulate the welding environment like vacuum in LBW, laser beam welding, and electron beam welding? This is a question, madam.
Yes. So in vacuum, whenever you are doing, so that the temperature of the vacuum environment. Hello, my audible?
Yes, yes, you can.
Yes, sounds like great.
You can continue.
Supposedly you are asking the working environment, as I already told, that you need to define the initial environment. Yes. So if you are doing some welding, so underwater, the buoyancy forces, all these will be different. Yes. So if you are doing in some vacuum environment, yes, that is where you are not keeping any air in it. Yes. So that is the initial temperature will be different. Yes, but supposedly you are doing at the same temperature also in the vacuum, no reaction can take place. Yes, so convection and radiation will be different. The heat losses will be different as compared when you are using in a non-vacuum temperature. So it is basically defined for the boundary conditions. Yes, am I clear? That is
Yes,
so.
yes, yes. Thank you, madam. Any other questions from audience, from participants? Acha. One question from Bikas Kumar. What will be the major criteria for the polymer and metal welding?
Major criteria is what?
What will be the major criteria for the polymer and metal welding?
Means what is the basic difference is two.
A major criteria for polymers and metal welding.
Means like dissimilar joining of polymer and the same metal.
So the question is not clear. Both he may be asking for both similar and dissimilar.
Dissimilar. For the dissimilar joining of metals with polymer, it is like what metal will be having properties temperature 25, where in the material the temperature is very good. Maximum temperature generally the transconduction temperature of the that is the operating temperature. So what is that? You need to move the temperature range and where the fusing is that you have to come to the ability. Like you have to put the area only to the metal part. And you have to avoid, you have to think that some gaps will be there. Yes, between the polymer and the metal. So the main is the temperature control must be there. And on the what putting the laser. Yes, from the metal. Will be reflecting it, but my metal will not be reflecting. So the efficiency laser, efficiency heat input absorbed by the material will mainly define how much gap because we already know the gap conductor will define how much it is being transmitted to lower the upper surface. So the convention, the infection, it can be controlled. Yes, the temperature, the interface can be controlled. So the heat transmitted from the metal to the upper polymeric material can be controlled. So and that is what the temperature is. So the multiple tasks are transmitted. So this is the main.
Okay. And because clarified his question, so like every metal cannot be welded to every polymer, right? So when we go for the polymer and metal joining, so how can we choose these two different, one is metal, one is polymer? What criteria we
That is
follow?
I told them
Okay.
that is the most of the polymers are transparent. They will absorb light at the without the editing. Okay, they're transparent. They are generally transparent to light. So the metal now the metal will be there. It absorb sufficient heat. It all that components like titanium are melting temperature is different now. But for a polymeric liquid, melting temperature will be. So that is not that does not conduct to the yes, the conductivity of titanium is very low as compared to the metal. So now it can be easily because the heat that is conducted to the polymeric liquid will be low. Yes, because the heat conduction is lower, the joint is low is more what we with the boiling liquid. Now if the titanium liquid is come to the heat and using for okay part of the heat connected to the surface. Yes, so that agreement between the boiling can be accomplished. Yes, so depends on the properties of the material, maybe the heat conductivity, the heat radiation, the elasticity of the material, all these parameters define. Yes, this is now the conductor area defines the solid. Yes, and the temperature is must. Like if you are using high scale, you are trying to find polymer material, then it is in subjectivity so high. Yes, it will try to conduct into the heat to the 80% electricity conduct. It might vaporize some heat. It might not cause the significant joining. Each type of things must be taken into consideration.
Okay. Thank you, madam. Thank you.
Okay. Thank you, sir.
Okay.
Thank you. Good day.
Thank you. So participants, next session will start at 2:45 p.m. and it will be on identification of different modes of welding during fiber laser welding, I think. Okay. So we will before 5 to 10 minutes you try to join this meeting. Thank you. Have a good. अभी तो आपका है ना नेक्स्ट अभी बात कर जो भी बात कर